Hi everyone, this is Anna Bergstrom, and we are going to take a brief interlude in our thermodynamics module to talk about RICE tables. So hopefully by the end of this video you will be able to teach someone else how to set up a RICE table and do it yourself, and then also be able to use a RICE table in a calculation. So what is a RICE table? It is unfortunately not a physical table with rice on it, even though, quite frankly, that sounds way more fun than what we are doing with RICE tables. What it is in terms of thermodynamics and chemistry is a clean way to organize reactions for equilibrium calculations. And R is in parentheses because sometimes you'll see it just as an ICE table with the reaction floating above it, and sometimes you'll see it as a RICE table. So what RICE stands for is reaction, initial, change, and equilibrium. And you would use it if you had a question, for example, given some certain geochemical process, what will the concentrations of each component be at equilibrium? You can also do it backwards and determine some equilibrium constants for some geochemical process. So we are going to dive right in and show you how to use them by doing some example problems. So this first example problem is starting with just some general reaction. So we have aqueous solutions of A and B. If we mix them together, we can yield 2C. And our KEQ here is 2.8 times 10 to the negative 7th. So if we initially have 4 moles of A and B, how many moles of each substance will we have at the when we reach equilibrium? So let's switch over and start writing this out. Okay, so we want to start out by writing our reaction. And in this case, we had a generic equation, A plus B yields 2C. Okay, so then after that, we need our initial concentrations of each of these substances. And we should note these are aqueous, by the way. Okay, so our initial concentrations are 4 moles of A and B, and the way the question was worded, it implies that there is initially 0 moles of C. We don't have any C when we start out on this journey. So then our change is going to be minus x, and because we have 2C here, it's plus 2x. So for every 1 mole of A and B, we're going to have 2 moles of C. And so at equilibrium, we will have 4 moles minus x moles of A, 4 moles minus x moles of B, and 2x moles of C. Okay, so this is great and all, but we still have unknowns and we need to figure out how to solve for x. So we can use our expression for our equilibrium constant. And so you'll remember, hopefully from previous lectures, that our equilibrium K is our products over our reactants to the power of the value out in front of each of these. So this is our concentration of C squared, because, let me make that bracket a little nicer, because we have 2C. And then in our denominator, we have our concentration of A times our concentration of B. Okay, and we were given a K value here of 2.8 times 10 to the negative 7th. Okay, so now we can just plug our equilibrium concentrations into this expression and solve for x. So we have 2.8 times 10 to the negative 7th equals 2x squared over 4 minus x times 4 minus x, so we can just simplify that out to 4 minus x squared. What you could then do is take the square root, solve for x, so on and so forth, but what we will find is that x equals 0.00106 moles. So how we would find these concentrations now at the end is for A and B. You'll remember up here we have 4 moles minus x moles for both A and B, which is 4 minus a very small number, so we effectively still have 4 moles of A and B, and then we have 2 x moles of C, so our concentration of C is equal to 0.00212 moles. So that is how you use an ICE table to determine your equilibrium concentrations of each substance. So that is one example, and I'm just going to do a couple more so you can keep watching. You can come back to this and play it whenever you need to, but we're just going to keep working through examples. So our second example is using gases and different phases. So the equilibrium partial pressure for the following reaction is 2.4 times 10 to the negative 9th. And the initial concentration of CO2 is 2 atmospheres. So what are the partial pressures of the substances at equilibrium? And given this equation, solid carbon plus carbon dioxide yields 2 carbon monoxide. Okay, so let's go back to writing and use our ICE table. And I will quickly let's see, open a new document to work with here. Okay, so we have our reaction, which is solid carbon plus carbon dioxide yields 2 carbon monoxide. Okay, so that's a reaction. Our initial partial pressures is we had 2 atmospheres of carbon dioxide, and we're assuming we initially have no carbon monoxide. And notice here, because this is a solid, we don't really have to include it in our figuring of this, so we can just kind of put a dash for our solid carbon. We're kind of assuming we have infinite supply here. So our change then, again, we're not worried about this solid carbon, but we have minus X amount of carbon dioxide and plus 2x, because we have a 2 here for our carbon monoxide. And then at equilibrium, we have 2 minus x, so 2 minus x, and 0 plus 2x, so 2x. And for our expression for our equilibrium partial pressure, again, we have our products over reactants, so it is the partial pressure of carbon monoxide, and because we have a 2 again here, it is squared. And then on our denominator, again, we're not worried about our carbon, we're only worried about our carbon dioxide, so it's the partial pressure of carbon dioxide. And there's nothing out front here, so it's just the partial pressure of carbon dioxide. And we were given the Kp value, and that was 2.4 times 10 to the negative 9th. So we can make that look a little nicer here. Okay, so we can plug these values from our RICE table in, and we have 2.4 times 10 to the negative 9th equals 2x squared over 2 minus x. And again, if we do some mathing and solve for x here, I'm not going to make you sit here and watch me do it by hand. We all know how to do algebra, hopefully, at this point. X equals 3.5 times 10 to the negative 5th. Okay, so our partial pressures of each of our gases at equilibrium, we can see here that X is a very small number. So 2 atmospheres minus a very small number is effectively 2 atmospheres. So we'll just say that essentially our partial pressure of CO2 has not changed, but we have 2x for our carbon monoxide. So our carbon monoxide at equilibrium is effectively 7, but if you use significant digits, it is 6.9 times 10 to the negative 5th atmospheres. So that is the second example using working with various phases and partial pressures with an ice table. So last example, solving for K instead of concentrations. So in this case, we want to determine K for the following reaction if we have 0.5 moles of X placed in a 750 milliliter container, and at equilibrium there is 3.5 moles of X. So given this reaction, 2X yields 3Y plus 4Z. So let's dive in. Okay, so the first thing that we're going to do is write down our reaction. So we have 2x yields 3y plus 4z. And initially, we were told that we have 0.5 moles of X. Okay. And we, based on the problem, it implies that we have 0 moles of Y and 0 moles of Z. So as of right now, we don't know how things changed, so we're gonna leave that blank and come back to it. But we do know at equilibrium that we have 0.35 moles of X. And because we know that the change is just the initial minus the final, we have effectively lost 0.15 moles of X. And we can do some stoichiometry here to figure out our change in Y and Z. So we know here that if we lose 2x, we're going to gain 3y and gain 4z. So our change in products here, so if we say change in y, is the stoichiometric ratio of y and z times however much we lost. So this is the stoichiometric ratio of y to z is 3/2 times how much we lost here is negative 0.15. So that means that we gained positive 0.225 moles of y. So plus 0.225 moles. And we can do the exact same thing for z. So our change in z is our stoichiometric ratio of z to x. So 4/2 times however much we lost of x, 0.15. So that's effectively 2 times 0.15, which is positive 0.3 moles. So plus 0.3 moles. And we can use this to go ahead and fill in our equilibrium amounts of y and z. So 0 plus 0.225 is 0.225 moles. Oops. Let's just write that over again. And 0 plus 0.3 is 0.3 moles. Okay, so now we can solve for k because we have everything we need to plug into our equilibrium expression. But we remember that we need to do this as concentrations. Right now we just have moles of a substance. We need molarity. So for each of these, it is, remember, we had a 750 milliliter container. So that's coming back into play here. So our concentration of X is the amount of X over the volume. So a 750 milliliter container is 0.75 liters, and the amount we have here is 0.35 moles. So our concentration of X is 0.467 molar. Let's make this a little neater. Maybe. Okay, and then we can do the same thing for y. That is 0.225 moles over 0.75 liters, and that equals 0.3 molar. And you don't need to see this for z. Our concentration here is 0.4 molar. Okay, so if we use our equilibrium expressions here, we know that our equilibrium constant is coming back to our stoichiometry, we have 2x, 3y, and 4z. So we have here products over reactants. So we have y cubed times z to the fourth all over x squared. So that is going to be 0.3 cubed times 0.4 to the fourth all over 0.467 squared. And what that comes out to in the end if you were to step through that, is 3.17 times 10 to the negative 3. So that is how you find an K value given some amount of information about what's going on in your reaction. So those are 3 examples of how you use an ICE table in various ways and some fun things about it. And now you can move on and use them in more interesting aqueous geochemistry problems.